In this example, I'd like to use the virtual work method to calculate the internal moment in a beam at a particular location. So what I'm going to do is consider a location, a distance a from the end of the beam here at this point here, and I'd like to find out what the moment at this location is. So I'd like to know what that's equal to. And what I'm going to do is I'm going to use the method of virtual work. So what I need to do is write the virtual work statement, which is the external virtual work is equal to the internal virtual work. So my external loading is this distributed load Q naught over the end of the beam here. So the external virtual work is an integral from, in this case, B to L of minus Q naught, because the load is pointing down, times the virtual displacement of the beam, so del V. So that's an integral with respect to x, is equal to the internal virtual work. So the internal virtual work is the true moment, an integral of the true moment as a function of x, and multiplied by the virtual curvature, so two derivatives of x, of the virtual motion, dx. And so I'd like to use this expression here to determine what m of a is. And to do that, what I'm going to do is I'm going to pick a particular virtual motion. So the virtual motion that I'm going to pick is one that looks as follows. So this is del v, this is x. I'm going to pick a virtual motion that is 0 out to a distance a, and then is a straight line with slope 1. The slope actually doesn't matter, all the way out to L. So this is my virtual motion that I'm going to pick. And so del V, if I want, I can write that in terms of x as the Macaulay bracket of x minus a. So that's the positive function. So the rotation field, or the virtual rotation field, is a step function. And the virtual curvature is going to be a delta function. So I'm going to plug this information here into my virtual work equation, and that's actually going to allow me to solve for the internal moment. So I'm going to get the integral b to L of minus Q naught x minus a. I don't need the Macaulay brackets since a, or x, is greater than a here, is equal to the integral 0 to L delta of x minus a times m of x dx. So on the right hand side here, I'm actually just going to directly get the moment that I'm looking for. And on the other side here, I'm going to get minus Q naught. I'm going to integrate x. I get x squared over 2, so that'll give me L squared minus b squared over 2. And then when I integrate minus Q naught minus a, I'll get plus Q naught a times L minus b. So that gives me the moment I was looking for, and I was able to achieve that by picking one particular test function. And note that if I want, I can rewrite the left-hand side here. I can factor this a little bit. I can write this as Q naught L minus b times minus L plus b over 2 plus a. So we can actually see that I'm actually getting the correct thing from the viewpoint of statics, because here I have the load, so that's like the force, and over here I have the lever arm. So the lever arm here goes from the point A out to the centroid of my applied load, and then I have this force F here. So F is equal to Q naught L minus b, and the lever arm is this distance here, a plus the distance to the centroid, which is the mean value of L plus b.